Ready to dive into the deep end of physics. We're tackling quantum gravity and the holographic principle today.
Yeah, we're going to try to make sense of some pretty dense stuff.
No kidding, but that's what we have these fascinating sources for. We've got excerpts from a PhD dissertation, some intriguing notes, and even a bit of Roger Penrose's Road to Reality to keep us on track.
It's a wild ride, for sure, trying to figure out how gravity, the thing that keeps our feet on the ground, actually works at the smallest levels of the universe where quantum mechanics takes over.
Right. It's almost like trying to mix oil and water. You've got Einstein's theory of general relativity explaining the big stuff like planets and stars, and then you've got quantum mechanics describing the tiny world of atoms and particles but trying to get them to play nice. That's the challenge of quantum gravity.
And that's where this whole holographic principle thing comes in.
Oh. Already. Sounds kind of out there.
Right. It's like, imagine watching a 3D movie. It feels incredibly real, but it's really just light projected on a flat screen.
Okay.
The holographic principle basically suggests that our entire universe, with all its dimensions, might be like that 3D movie, just information encoded on some kind of distant surface.
Whoa, okay, hold on. I'm trying to wrap my head around that one. So we're talking about the universe being like a giant hologram, but before we get too far into this dissertation dives straight into black holes. I always pictured them as these like cosmic vacuum cleaners sucking everything up, but they're important for understanding all of this.
Oh, they're totally crucial. They're like the ultimate physics laboratory because they're so extreme. We're talking incredibly dense objects with so much gravity that not even light can escape.
Yeah, intense stuff.
But here's where it gets even weirder. Stephen Hawking discovered that black holes actually emit radiation, which means they slowly evaporate over time.
And so they disappear. But what happens to everything they sucked in?
Yeah.
That doesn't just vanish, does it?
That's the million-dollar question. It's like burning a book. The information in the book doesn't just disappear. So where does it go when a black hole evaporates? That's the information paradox.
Okay, yeah, I see the problem.
And one way physicists have tried to tackle this paradox is with string theory, which says that everything in the universe isn't made of particles, but these tiny vibrating strings.
Strings.
Yeah, it's like this. If you think of particles as notes on a piano, then strings are like the whole instrument. They can produce a much wider range of sounds, or in this case, physical phenomena.
Interesting. So instead of just individual notes, we've got a whole orchestra going on.
Exactly. And this dissertation mentions something called an effective action equation. It's a really complex equation that basically shows how string theory could modify Einstein's equations to work in the bizarre world of quantum mechanics.
So it's like we're taking Einstein's classic theories and giving them a quantum upgrade.
It's more like proposing a whole new model of physics that encompasses both the big and the small.
Okay, got it.
Yeah.
So how does this tie back to the holographic principle?
This is where it gets really interesting. The dissertation talks about something called the ADS/CFT correspondence. It's a very powerful mathematical tool.
Let me guess, this is where the math gets really intense.
It does get pretty heavy, but bear with me. Imagine a fishbowl. You can see the fish swimming inside, but you can also see their reflections on the curved glass surface.
Right.
Well, the ADS-CFT correspondence is kind of like comparing that fishbowl to its reflection. It suggests that a theory of gravity in one kind of space might be equivalent to a completely different theory on its boundary.
So we can learn about one by studying the other.
Exactly. It's a way to create a simplified model that helps us understand a much more complex system. And this dissertation uses some seriously advanced math to see if this holographic principle holds up under scrutiny.
Okay, you're gonna have to refresh my memory on some of that advanced math.
Don't worry, we'll get there. The important thing is that physicists are using all these tools to try and unlock the secret of the holographic principle and what it might tell us about the true nature of reality.
So it's like trying to understand a car engine by just looking at the exhaust, huh? But you mentioned we have another tool to help us on this journey, Roger Penrose's Road to Reality. I've heard it can make even the toughest math concepts understandable.
It's a great resource. Yeah, Penrose really lays out a fantastic set of tools to help us wrap our heads around this stuff.
And he starts with something called the Riemann mapping theorem.
Right. It's all about understanding complex mappings and distortions.
Okay, sounds a bit like we're entering the matrix here. So what is this theorem all about?
Well, imagine you have a treasure map, but it's printed on a stretchy rubber sheet. You can twist and pull that sheet in different directions, and the Riemann theorem basically helps us understand how to do that without ripping the map apart or making it impossible to follow.
So we're talking about the universe being like a distorted treasure map.
Kind of. It's about understanding how things change shape and how we can still make sense of them.
Okay, so not quite the matrix, but still pretty mind-bending. And Penrose doesn't stop there, right? He also talks about Fourier decomposition. Didn't that come up in calculus class? Vaguely remember that?
Yeah, it's all about breaking things down into simpler pieces. Like, imagine listening to your favorite song. With Fourier decomposition, you can separate the vocals, the drums, the guitars, each instrument, and analyze them individually.
So we're like dissecting the universe's music one instrument at a time. That's cool.
It's a great analogy. And then Penrose introduces us to hyperfunctions.
Hyperfunctions, those sound intense.
They're a bit more abstract, yeah. But they help us deal with situations where things aren't so smooth and continuous, which happens a lot in the quantum world.
Right, because the quantum world is all about things jumping around and being totally unpredictable.
Exactly. So we need these special tools to describe how things work down there.
This is definitely making me appreciate how weird and wonderful the quantum realm is.
Yeah.
But speaking of weird and wonderful, how does this addendum you mentioned fit into all of this? We were talking about how gravity might actually shape time and entropy.
Oh, this addendum is fascinating. It really highlights how gravity acts like a sculptor of time and entropy, especially in extreme environments.
A sculptor of time and entropy. So instead of chiseling away at marble, gravity is like the artist of the cosmos, shaping the very fabric of existence.
Exactly. It's like how a river flows. The water is constantly changing, but the riverbed shapes its course. Gravity is kind of like the riverbed of the universe, influencing how time flows and how entropy unfolds.
Wow, I never thought about it like that. That's really profound when you think about it. So black holes are like the ultimate expression of this, where gravity's influence is the most extreme.
Precisely. And that's why they're so important for understanding these concepts. Black holes are where our current understanding of physics really starts to break down, which is why these ideas of quantum gravity, string theory, and the holographic principle are so exciting and potentially revolutionary.
So we've got these massive objects shaping the universe in this really profound way. And at the same time, we're thinking about the possibility that everything we see and experience might just be information encoded on some distant surface. It's kind of mind-boggling.
It really makes you question everything we think we know about reality, doesn't it?
Absolutely. It makes me wonder if this holographic principle is true. What does it mean for us? Are we all just projections? It's a pretty wild thought.
It's a huge question. And it takes us beyond physics into philosophy and even spirituality. It makes you think about free will consciousness, the very essence of what it means to exist. If our universe is like a giant hologram, is our consciousness also part of that projection?
Okay, now my head is really spinning. I started this deep dive hoping to understand the universe a little better, and now I feel like I have even more questions than before.
That's the beauty of science though, right? Every answer leads to more questions. It's all about pushing the boundaries of what we know and venturing into the unknown.
This dissertation definitely emphasizes that. It keeps saying that this is all an ongoing journey. We're still searching for those missing pieces of the puzzle.
And that's what makes it so exciting. It's like we're explorers setting sail for uncharted territories, driven by this thirst for knowledge and understanding.
Who knows what we'll find out there?
Exactly. So if there's one thing to take away from this deep dive into quantum gravity and the holographic principle, it's this. What if everything we perceive, everything we experience, is just a glimpse into a far grander, more mysterious reality than we could have ever imagined?
It's a truly awe-inspiring thought, one that I'll definitely be pondering for a long time. Thanks for taking us on this incredible journey.
It was my pleasure. Thanks for having me.